Finished our first evening of soldering work on the top portion of the unit. Our input board here, the 12AX7, had these new 0.02 microfarad capacitors, which replaced these right here, as well as one 50 mic that is now on the back of the board right there. Those are the only components that were done on this board. All of the other components tested out good. There was no need to do any further work on this unit. I'll check the wiring, just try to move stuff around, do verification, make sure everything's copacetic, and then reassemble this. That's done. As far as this goes, we had a mini lytic here, mini lytic there, has been replaced. We had 3 of the electrolytics right here. That was for the filter for the power supply. Those have been replaced, and this is a 0.5 or 0.47 microfarad capacitor. This was originally a waxy right here. This is a very old Sprague cap. This has been replaced with a polyester, which is only just a little bit smaller than that, but when you consider it's polyester and not wax, is pretty cool. But this one is good for 630 volts, much higher voltage rating. So that one went in there, and just slightly smaller enough that I could fit these in very nicely, and these are nice and taut. This is the center ground right here, the roll ground to common post. A lot of stuff grounds to this common post here. There are a couple separate grounds, but it's not really crazy. I think the grounds are divided into just a couple of sections on this unit, but I'm all soldered out tonight, so I'm going to do the rest of these electrolytics tomorrow, and that should finish it up. But because these are done and the tubes are tested, we'll be able to start testing the power supply, at least without the rectifier, and just seeing what we got, which we can anticipate higher voltages, and then bringing in the rectifier and going from there and start testing the circuits along the unit and then getting everything working. So that's where we are right now. Just looking at the values of the top components we replaced, we see that the 2 capacitors had, as far as capacitance goes, weren't far off. It was okay. But like I said, leakage at 150 volts and 100 volts. The 50 microfarad capacitor actually read at 75. It's off by a magnitude. And leakage was at, I say less than 3 volts because I can't measure less than that, right? So if we look at how that equates into a circuit, and granted this is for a different amplifier, but this is awfully close. We can see on this circuit that the plates are seeing 130 volts. And if we were to just pretend for a minute that we saw those values that I had shown, then one of those, and yes, this one shows 0.01 for those coupling capacitors, but one of those capacitors would be leaking DC into the next circuit, and the other one would not, right? Depending on the input voltage. So there would be one channel that may be acting funny and dragging down the circuit, the voltage, and a channel that would not be dragging down the voltage. So this is very strange. Things that you notice that happen in an amplifier that you simply just can't identify. It's caused by things like that. And the other one was obviously that 50 microfarad capacitor that was reading 75 sits right here, and this sets up a circuit for the cathode on on this particular 12AX7. And obviously the values are different here, but you can see that these components are extremely out of specification. Amp can't possibly sound like it did back when it was made with components like this so far out of spec. And that's why we've taken these components and we've replaced them with components that are within specification, and this amp should work properly for a good long time. I'm generally one of those people who could be accused of doing shotgun replacement of electrolytic capacitors and other types of capacitors and these types of circuits, and well, I do measure all of them as I replace them, and if you look at these values, you'll see that the capacitors, once again, were quite terrible. People will tell me that, you know, it's somewhat premature to go into these things and replace them, and these things work just fine. I hear that a lot from ham radio operators in their old equipment. My capacitors are 60 years old. There's no need to replace them. And their idea of working is how it works to them. You know, the fact that they may be pulling down voltage, or the quality of the device may be suboptimal because it's been running like crap for so long, they just assume that that's how it's supposed to work, has absolutely nothing to do with the fact that when you have a component that's designed to be an open and it's in fact shorted because of time, that component needs to be replaced. This is a testament to that. I want to point out, I found 150 in the circuit that was removed, one of those 50 that actually measured 119 microfarads. I thought that was pretty cool. The other one measured 70. The other one measured 75. But these are the readings from the ones that were pulled out. The 16 and the 210. Those 450 volt rated capacitors topped off at 50 volts and 25 respectively. So way underrated in voltage. Probably had a lot of leakage going on in this amp, so it's going to run real nice once I get the rest of those Sagamo caps out and get this amp back together. So we have the right half of the lower portion recapped. All of those capacitors have been replaced. Last night I did the electrolytics and the filter and the vibrato, as was shown. But now we're doing the aqua ones, and they've all been removed, and we've got quite a pile here. But you know me, I've got to test them, and I refer to this as the right side, and these were the ratings that were removed at 600 volts. And if you look at it on a capacitor tester, with the exception of the electrolytics that were off the wall, these ones show to be well within spec. And once again, we see that where it fails is on leakage, that they rated for 600, most of them failing at 50 and 100. By comparison, however, what I'd like to show is one of the new capacitors in place here that replaced one of the old ones. And I'm going to hook it up to the tester here, and I'm going to crank this up all the way to max voltage, and we're going to watch from 3 all the way up, get it up to 100, 50, this 250, 350, 450, 500, 600 volts, right? And that's on the lowest setting. That's, you know, that'll detect like 3 microamps or less. So that's what we mean by no leakage, you know, no leakage. I'll turn it back down to 0 and obviously discharge so I do not kill myself. But when we hook up those and we see that it was slowly opening up at 50 and then at 100 the eye was closed, that's leaking, it's garbage. This is what good is. So now you've seen the comparison between a good capacitor and a bad capacitor. So what we're going to do, we're going to finally knock out this other side here, and then we got to go through and check and inspect all of our soldering, make sure we didn't short out anything or have any crap that got caught, you know, inside some piece of wire, cable, and what have you. Very nice to dress. Things are obviously a lot smaller than their older counterparts, so let's get to work. At this point, I've swapped out all the capacitors. The recap on this amplifier is done. We're going to be checking, making sure everything's cleaned out. All this kind of garbage here, this is the stuff that you want to make sure doesn't short out anything. We'll blow this thing out. Here's all the capacitors that were removed from this unit. There's quite a few capacitors for a guitar amplifier. This is quite a lot. The ones on the left that were pulled out were just like exhibited the same qualities as the other ones. The actual values weren't far off, but the leakage, the breakdown voltage was quite low, ranging from 150 down to 50 volts. So this concludes the capacitor swap out portion. Now we're going to get everything back together, not inside the case, but we're going to mate this up to the top portion of the amp. We're going to start doing voltage measurements and see what we got. So what we got here is a complete amplifier all hooked up without the rectifier. I'll explain later. But the amplifier is completely wired. We have the top portion of the amplifier with the 12AX7 to split the channels. We have the signal cable, the coaxial signal cable running down to the bottom. We have all of the controls and the heater elements, the heater, power, what have you, all running down with this separate cable here. The speaker output is connected in turn to this 8 ohm dummy load. And then I have my oscilloscope probe also tied to that probe. So we'll be able to monitor in my hand tach. Naturally, I've disconnected it for the power on. I feel as if it's not necessary to blow up my oscilloscope in case something goes wrong. So I've got that disconnected. The reason why I don't have the rectifier tube in is I do not want, at this time, any high voltage DC in the system. I just want to do some tests. The reason why I have the tubes in, the tubes are basically going to act as very nice looking low glowing light bulbs. I'll be able to test the heater, be able to work the power transformer, see a nice glow, do some measurements, basically measure the power supply and what have you. When I'm satisfied with that, then of course we'll put in the rectifier and then we'll be able to take some other measurements. This is sort of a step one that we're going to do. I'll also note that this is not directly connected to mains power. You know, this power switch will be turned into the on position as plugged in, and it goes into an isolation transformer. So we'll be powering up the unit obviously from an isolated power transformer that is not directly connected to earth mains, as we should be doing. Some people use the light bulb method. I got a little confidence in this one. I do have a fuse in line, and I'm not actually touching the chassis when I turn it on, and the chassis is physically disconnected from earth. It's floating. There's no reference. So that's what we're going to do. That's what we're going to do next. Among the voltages worth noting, it's a good idea. When looking at the schematic, you could see that the pilot light is a good indicator, or at least it brings you in a proximity of what the pilot voltage is doing. Come right off the pilot, and I've set this up because I'm making a movie and it's really dangerous to do this if I didn't pre-set it up. So come off here, look at the pilot, and we see 6.66, which stands to reason since we don't have a rectifier tube to load it down. Pretty close to the 6.3 we expect. So gives me a good indication the power transformer is doing good. Other voltages I've taken also show it to be good. So we'll continue on and put in the rectifier and see what happens. As a final measurement, we come out with about 6.6 volts to serve the heater voltages for AC purposes within this amplifier, as well as 6.6 volts that comes through this cable to serve that 12AX7 back there, as well as the input to the rectifier here. Obviously the same heater voltage applies, as well as a reading of 557 volts AC going into that rectifier. That'll be the final measurement for this power transformer. This is going to be the game changer. Now we got the rectifier in. I'm going to set this to DC. Okay, I've got the oscilloscope plugged in. This is reading the power off of the rectifier, so we don't expect to be any power to be produced when I turn on this amplifier. By power I mean voltage. And what we're going to do is we're going to fire it up. We're not really looking at the oscilloscope. I just connected it up, and we're going to see eventually the rail climb. This is the output of the tube. We're going to come back and look at the voltages now that we have some load on here and see how that dropped. So expect some change here. It'll take a minute as the tube heats up. Oh, there we go. You see it kicking on. I see coming up to 271. Obviously I'm going to have to take some measurements because I don't know what it's supposed to be yet. But it's a start. Things are working. I'm going to have to measure through and see what's going on here. So let me take a look and make some measurements. I've temporarily broken away this bias resistor here to do some experimentation to change the cathode bias. Obviously I'm not satisfied with making a necklace full of resistors. I know that as I get close to the amount of bias that I need, you know, erroring on the side of caution is really nice for testing, but it doesn't say anything about what we should be setting up the tube for, and that's why we got to break out the ammeter. That's what I'm doing now, and a little bit of mathematical computation shows that my resistor necklace here laying on the floor is a bit overzealous, and I'll explain why. Looking here at the 14 watts of full power I would expect from the 6V6. Shows that given my plate voltage, which sits around 310, for this, in this scenario, I would expect 44 milliamps at 100% of what this tube could provide, right? 70% of which I've seen at least discussed in guitar amplifier lore to be an accepted value. So I'm just using that as criteria. It would be 30 milliamps. I found the left tube was drawing 15 milliamps, and the right tube is drawing 13 milliamps at rest. And this tells me that I'm obviously got way too much bias, and there's not enough current draw here. So what I'm going to have to do is shut this down, drop the bias a little bit, and see if we could get a little bit more current draw. But the calculations need to be redone, because I know when we get current draw, what's going to happen is we're also going to see that this voltage is going to drop, this plate voltage, as the excessive current draw brings down the entire circuit as well. So every time we do this, we need to recalculate. So that's what we're going to do next. I think the easiest way is obviously going to be the removal of simply one resistor from this circuit. That's what we'll do now. I came to the conclusion that basically what we got here is a 14 watts with a plate voltage sitting around 270. We would come out at 50 milliamps at 100%. For these tubes, we won't run them at 100%. 70 seems to be the effective standard. And using the resistor that was with the amp, I have come to find out that what we're seeing is, for the left tube, we're seeing a current draw of around 33.7, and the right tube we're seeing 31 milliamps. The bias voltage, as measured right there at the resistor, is 14.87. I do have to point out that the method that I'm using is somewhat unorthodox, as my meter here, my ammeter, is coming off the center tap of the output transformer to each tube respectively. So I am not accounting for the resistance from the edge of each end of the coil to the center tap. That means that this value is slightly skewed. I have a device that measures this more accurately. I haven't taken it out right now. I'm just trying to get an effective reading. That would be more appropriate if this amp were standing up and I were taking measurements from the top. I'm not doing that. But what I see is everything looks pretty good. Been doing some tests, looking at the vibrato circuit, which I'm clipping on and off with a cable that I have provided over there. But I noticed that when the bias is changed for the power tubes, that the plate voltage is taking quite a drop. And what I'd like to do is just for being thorough, I want to drop another rectifier in here, and also check the power transformer to see if the drop is the voltage on the AC side of the power transformer, or if the voltage is on the output of that rectifier. So we're going to take a look at that as well. Again, I find that stability comes from migrating away from the isolation transformer. The number on the left is the number of output tubes in the system. You could see with none, the AC going into the rectifier was 555. And I introduced one tube, it dropped to 532. But when I introduced one tube and took it and put it on the mains, it jumped to 542. When I put two tubes in on mains, it would drop down to 537. But then when I left the two tubes in and put it back on the isolation transformer, it dropped down to 526. And obviously, you could see that the DC suffered accordingly. That being said, I was able to stabilize the amplifier even further once I took it off the isolation transformer and got it on the bench on the mains power. So that was a good thing. I think we have the tubes relatively matched, off by 2 milliamps. I think it's close enough. Running at 70% duty cycle. I'm going to run a couple other tests, but I think it's time to put this thing back together and give it a try.